Okay, cool. So when we're using the chain rule, what happens is we're trying to take the derivative of f of g. We've got d dx of f of g. The d dx means derivative. So please don't ever say that the d means derivative. The d alone means difference. d dx means derivative. Okay? So we got the derivative of f of g. Per the chain rule, we're supposed to, so that means we're taking the derivative of sine of x cubed. The chain rule says to find the derivative of a composite function, what you do is you first take the derivative of the f function. Well, I'll just tell you that if the function is sine of x, the derivative will be cosine of x. So I'm not giving you any reason for that. But basically, if you were to do something similar to this right here with sine of x, you end up with a discovery that the derivative is cosine of x. For our class, we don't have to keep doing that, so we'll just jump to the result. So let's see. F prime is cosine of x. So the chain rule says I take this derivative, there it is, f prime, plug into that the g function. So I did, cosine of x cubed. Then I multiply by the derivative of that g function. That's the chain rule. Questions about this step using the chain rule?
Yes, please.
2 points for Hayden for asking the question everybody wanted to ask. Okay, perfect. That was the look I was getting, and I was just waiting. And so it's really important that you maintain equality throughout this class. So right here it says this is equal to this. So the first step is we're going to apply the derivative operator to this side, which means to maintain equality, we must apply the derivative operator to this side. So these two lines should look nearly equivalent, only difference being we ddx one side, we ddx the other side. Is everybody okay with that? Awesome. Okay, when I look here, I'm like, okay, how do I find the derivative of sine x cubed? Well, I don't have any idea. But I remember the chain rule, which says if you have a composite function, here's my two pieces of the, no, sorry, here are the two pieces of the composite. You can take the derivative, f prime of the f. So the derivative of sine is cosine. But then instead of plugging in the x, you actually plug in the g. So instead of cosine of x, it becomes cosine of x cubed. That's what the chain rule is telling you to do. Find the derivative of f and plug into f the g function. So the derivative of f is cosine. Plugged into that, the g function, that becomes cosine of x cubed. Question. Then the chain rule says you now multiply by derivative of the g. So the g function is x cubed, so I've got d dx of x cubed. Since d dx means derivative. Question. Cool. Right here you can use the power rule. d dx of x cubed, bring down the 3. X again, 3 minus 1 is 2. So this is the derivative of this. Meaning if you plot this on a graph, go to any point on this graph, you can use this formula to find the slope on this graph. That's what derivative means. So literally in Unit 1, whenever you would see a graph and then they'd say, which of the following is f prime? What they had done is they'd taken some function like this, found the derivative just as I showed you, and then plotted this one. So that's how they come up with the plots. Or like here, where I showed you all three. Same thing. Take a function, find the derivative again. So, questions? Awesome. Back to here. All right. Okay, when I learned calculus, I was taught the power rule, I was taught the sine rule, cosine rule, et cetera, And then after practicing those a little bit, the teacher taught me the chain rule. And then the chain rule kind of sits in the center. And like all the other rules kind of fit around the chain rule. And they all interact with each other via the chain rule. So the chain rule is the kind of center idea. I found that to be a difficult way to learn. Like the individual rules were easy, but once we had to combine them with the chain rule, it became difficult. However, the first couple of years I taught calculus, I didn't know of anything else to do because that's what I had been taught. But on the third year, it suddenly just occurred to me that, hey, wait a minute. If I combine mathematically the chain rule and the power rule, right here, the chain rule and the power rule, I can create a better power rule. And it makes using those two rules easier. So that's what I've done to help you. Okay? So I'm not good at teenage slang. So you have the regular power rule. So what do you call something that's like better? Or what is it? Oh yeah, so this is, so I've created for you. Let me draw it. I don't like that screen size. Hold on a second. So I have created, let's see right here. What's the one? So new sheet. Why does it do that, you stupid machine? I'm very frustrated. I like that better. So I've created for you the dope power rule. And it looks like this. D over dx. So if you're trying to find the derivative of a function that has the following form, okay, the regular power rule would say x, right? Well, because this one is dope, you can use it not just with x, but with anything. Okay? Now, mathematically, anything usually is written as f of x. But I found it easier to help you learn by inventing my own symbol. So this is my symbol. You'll never see it in a math book, but I think it communicates well. Anything. Just whatever. Okay? To a number. So if you have the derivative of anything to a number, that is equivalent to, now this part will look just like the power rule. Bring down the n, multiply by that anything. Keep in mind, these are the same anything. It's not two different things, they're the same. So whatever this is, it becomes this. This is n minus 1. And then the additional part, now that I've combined it with the chain rule, is you must do d dx of the something. So that should feel a bit like the chain rule we had back here. Because remember on the chain rule that I wrote down, we had that g prime on the end. That's why my dope power rule, now I feel like I'm violating some policy calling it the dope power rule, has the d dx on the end. Not enough. There's like one thing in there. So thank you. Questions? So as we do problems, we just use this. But keep in mind, this has combined power and chain together. Okay? There will be a few cases where we'll use the chain rule all by itself. It's just not very common. Usually it's used in conjunction with something. And I found this for students to be much easier to learn. I've also combined the sine rule with the chain rule, the on and on and on. Okay, so I have the whole list of dope rules. No, that's the wrong word. I don't know. Okay.
Is the derivative of anything on the far right side, is that being multiplied by?
Being multiplied.
Okay.
Like it's n multiplied by this, multiplied by this. Is that what you meant?
Yeah.
Just don't make this mistake. This is not d times whatever, it's d of whatever. So it's the difference of this divided by the difference of this. Or you can just think of it, Maya, as derivative of, but not multiplication. Question? No. We'll pause for a minute. Anybody else? Okay, so let me pass something out. This is printed on cardstock. You take this. Maddie knows what I'm going to do. And you combine it with, yeah, there you go. Pop that out for me. You combine it with this. This is all planned ahead of time. Like so. And it all fits. See, this was plain paper within sheet protector to indicate importance. This is now cardstock within sheet protector to indicate more importance. And somebody always asks, must we memorize it? And my only response is, well, there's no reference on the AP test, so yes, we must. So, okay, excellent. So pass these around. These are the complete set of better rules. Somebody yesterday said we should call them the sick, nasty rules. Can't keep up with teenage slang.
Can I hear one?
There was a year where everyone was like,
Apologies.
trying to
Yes.
Thank you.
Never leave
Sick,
Rachel out.
nasty.
Sick, nasty rules, yeah. You will not find these on Google, so my invention. All right, another handout. Great. All right. I pretty much got the Chase and Austin.
But I don't really know if
Sounds like
essentially, yes.
oh, my bad. I'm excited to see that your grammar is about as good as mine. So.
we started reading. Yeah. Ellie. Say watch out. What is that?
How do you know that?
Watch out. I hear you say.
Are you Chinese?
I'm just trying to. Watch out. Now, Ellie. Hashtag gift of tongues, people.
你的 account 他的中文是很好，他的
你好。The Tesla speaks Latin. Professor Sans Thai.
Write that down, please. Write this down on your notebook. Now write this down in your notes. Okay. As soon as you have that written down, you're going to look at me so you all hear the warning. That's just number 1 on that buff sheet. So. Okay, here's the warning. Drew, look up for just a minute. Tessa, happy. Awesome. Here's the warning. Okay, for the next several days, what we'll be doing is very, very simple. We are starting with a function. We will be applying the sick, nasty rules, okay, to the function in order to come up with a new formula. The new formula is f prime, the derivative of the function we start with. Okay, here's the warning. To get points on the AP test, you must use the equal sign properly. So as we do this process over the next several days, you must use the equal sign properly. Okay? If you don't do that, you won't get points on the AP test. Simple as that. Next thing. This process is ultimately really easy for most people to do, sincerely. If I were to poll students, this is the weeks of the year that most people like the best from a standpoint of it's just the most straightforward. Okay? It is not the most rewarding per se. The most rewarding is April, when you really are putting it all together. And you can really answer really tough questions. Okay, that's the part that is most memorable. But anyway, okay, to learn this process, this idea of how to find a derivative properly, you must write what I write. If you don't, you'll get mixed up. I guarantee it. If you try to take shortcuts, you'll get mixed up. So my rule is simple. If you write what I write, and you come to me and you're like, hey, I'm a little confused why I'm not getting the right answer, and I can see immediately that you are following my method, I will help you until you understand. If you show me your work and I'm like, where did you learn this? And they're like, well, I saw this, this way is better, and I'm like, I will hand it back to you and say, you're on your own. Because if you don't follow my method, I can't help you. I can't follow some invention of yours. Okay? Questions? To motivate you to do that, I have been known in past years to once in a while walk up to someone like this who has a nice notebook, and so for example, you do not do the work here. Yeah, impossible. You do the work here. So I look at their work and I go, okay, I turn the page and like I'm just scanning straight down the page looking for proper notation. Don't go across, down. Everything looks good, it's easy to read. I commence this. Is that the right hand signal? Like this? Like this? Is that right? Oh, like this, yeah. Well, just to her. So so I give her a bunch of tickets, like, good job, Sarah. Okay. I go to another person, and it's like, I don't know what that is, but it's not what I taught you. Move on. Understand? Okay. Question. Okay. Awesome. So here we go. So step number 1 is easy. We just want to take the derivative of both sides of the equation. So we ddx both sides. So we ddx both sides. Okay, question? Awesome. Oh, please.
Are you just doing, which one are you doing? Which rule?
Oh, gotcha. So no rule on the sheet yet. What we're doing is ddx means derivative. So we are differentiating the left side of the equation. That's the word you use. Or you can say we are taking the derivative of the left side. Algebra requires that if we're going to maintain equality, we must do the same operation to the right. So we haven't actually applied a rule yet. We're just differentiating both sides. So this sounds kind of dumb, but the goal is to find dy dx. And in reality, we have found what dy dx is equivalent to. This is some function. The derivative of that function is this. Okay? This just isn't very useful because with the ddx operator, you can't plug things into x. It's not allowed. So we need to transform this into something more useful. In other words, we need to get rid of the ddx operator. You do that using the list of sick, nasty rules. Okay. Gotta come up with a new term every time I say that. You guys all wince. Okay. So look at the sheet. Look at the sheet. Look down. There are 16 rules. Okay? Look at the left side of each rule. The left side of each rule. You're trying to find a rule, because notice how the left side all says ddx, 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 ddx. You're looking for a rule on the left, or over here on the left, that fits our situation. So I want everyone to raise their hand once they find it. So we got ddx of this. Only one rule out of 16 will fit. Talk to each other, raise your hand when you can find the rule that fits ddx of this. For example, it is not, back here, that's too many pages back. Let me load another copy. Hold on a second. Like it's not the ln because we don't have ddx of ln of something. It's not the exponential rule. We don't have ddx of something to a number to something. So hands up. Who knows what rule works? Show me your hand. Show me your hands. What rule works? Only one of them works. What is it, Sarai?
Maybe the power rule.
So the power rule fits because the power rule says this. D of something to a number over dx. And that's what we have. These two are a perfect match. How many had it? Show me. 0.2 for Sarai. You wouldn't want me to talk more about it. Awesome. Okay, now we take advantage of equivalence, like what's equal, right? So we have these two things, same thing. So if these two things are essentially equivalent, then the rule says if you have something that looks like this, you may rewrite it as this. So I apply that here. So let's see, the n is 3. The stuff being raised to the n is the base. The base is negative 3x to the 4th plus 4. The new exponent would be 3 subtract 1. And then I multiply by ddx of the base. So I need to move this over just a little bit. Whoops. Wrong pen. So let's see, ddx of the base. No exponent, just ddx of the base. Questions? Please, Rachel.
Wait, you said it's to ddx of the base, but how is negative 3x to the 4 plus 4 the base?
Gotcha. So right here it was ddx of this base to this exponent.
Okay.
So when you have this type of function, this is just referred to the
Oh,
base. That's
okay.
all. Does that make sense?
Yeah.
No, good question. 2 points. Who else? Awesome. Okay. Our goal is to get, dy dx equals just a formula. So we still have a ddx here. We got to get rid of that. So the process just repeats itself. We go back to the rule sheet, and you look down the rule sheet, and you find a rule that fits this. ddx of this. Now, one caution. The power rule does fit this situation, because you could think of the exponent as being 1, but I don't ever use the power rule when the exponent is 1. because it doesn't tend to be very helpful. Like there's a better way. So don't pick the power rule, but raise your hand when you find the other rule that fits this situation. You can talk to each other.
I have a question.
Oh yeah, please, Mikhail.
Why is there no 3 exponent on the second one?
Over here? Is
Yeah.
that what you meant?
Yeah.
So the power rule says if you've got ddx of stuff to a number, that's equivalent to number, stuff, new exponent, ddx of just the stuff, not stuff to an exponent.
Okay.
Does that make sense?
Yeah.
2 points. Hands up. Who found the rule? Come on. Few people. So what I mean by left, Avery, is this. I've got 16 rules. Each of the 16 rules has a left and right side of the equal. So I'm looking here, 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 and here.
I was just looking at the left.
Gotcha. That makes sense. So looking for which of those matches up with that. I don't look here because there's no ddx operator here now. Hands up again. Who sees it? A few people. Let's go Noah.
Is it the addition rule?
The addition rule is a perfect match. If your hand was raised and you were thinking addition, show me your hand again. Point. 2 for Noah. Question. So the addition rule says if you have ddx of 2 things added, you can change that into ddx of each individual piece. But caution here, so eyes on the board. Look up how they just a moment. Right here it's got 3 multiplied by this, multiplied by this. So those 3 things are being multiplied. Per the addition rule, this is going to become 2 separate things. But both separate things must still be multiplied by the 3 and by this. So make sure you write a parenthesis. That has been an extremely common mistake. We have dy dx. If you don't like dy dx, you can call it f prime. Essentially means the same thing. So I'm just rewriting this. Oh, warning. Don't do this. Okay? Write it out. Don't do this. If I'm checking your pages and I see this, I do this. Hadley got it. Okay, good. Yeah, just move on. So no ticket. So here we go. 3, negative 3x to the 4th, plus 4, squared, parenthesis. Let's change color to emphasize the importance of the parenthesis. Then using the addition rule, this becomes ddx of negative 3x to the 4th plus d of 4 dx. Question? Any chance to catch up? Any part of that bothering anybody? Adley, please.
So that's not the second step. Where did you get that?
This one here.
Yeah.
So what I did, so you're okay on this line?
Right.
So I've got ddx of this. The addition rule says if you have ddx of one function plus another, keeping in mind that if we call this f of x, it's not the same as this f of x. This just means ddx of 2 things added. The rule says you can rewrite it as, I think the sheet says f prime plus g prime. But f prime just means ddx of f. And g prime just means ddx of g.
And that's the second.
And that's what this is. Did that answer your question? 2 points.
Wait, how
Please.
is that g? Because I feel like I understand the rule, But we're only looking at one function.
So it's a matter of perspective. This says d dx of one thing plus another.
Yeah.
So as I apply the rule, I'm just temporarily thinking this to be f and this to be g.
Okay, so we use the addition rule in addition to using the power rule?
Oh, outstanding. 2 points. Yeah, hey, the way most of the problems will go, once in a while you hit a problem where one rule is sufficient. But most of the time it's a combination. And that's the reason for this, is most of the time it's all these rules, and they're all kind of working through the chain rule. And then I just put them together to make it go quicker. So,
Okay.
2 points.
So the only reason that we're doing these rules is to get rid of that derivative deal.
Yeah, you're trying to get rid of the ddx operator. The rules provide a way to find something that is equivalent to this without the ddx operator.
So you're like simplifying.
In a sense.
Kind of.
Really what you're doing, Brennan, 2 points. But really what's happening is you are applying this process to a much more complex function. We just don't want to do all these steps. So this little shortcut method accomplishes that. So, for Brennan again, any questions? Solid. Okay, so look here. Look down the sheet. Find the rule that applies. Raise your hand when you can see it. This is the process. This repetitive, find a rule, apply, find a rule, apply. There's really nothing more to learn for the next several days. Just practicing enough different examples that you don't get confused. So, find the rule. Raise your hand when you have it. Elijah's in, Kel's in, Maddie's in, Brennan, Isaac, Whitney, Allison, Rebecca. Talk to each other. Find the rule that fits. Find the rule that fits. Hands up. Hey, who thinks to know what rule works? Come on, show me. Elijah. Power rule. So everybody watch. Everybody, look. There we go. Okay, if we had d dx of x to the fourth, the power rule would fit. If there were d dx x to the fourth, the power rule fits perfectly. With the extra 3, it actually doesn't. Okay, so we have to use another rule first before we use the power rule. So 2 points for Elijah. Who sees the other rule that fits here? So Drew?
The exponential rule.
So let's check that one. So exponential says you would have some number, like 5 or whatever, being raised to some exponent. So point for Drew, but that one doesn't fit either. This is -3 multiplied by x to the fourth. So let's go, Mikkel.
The product rule?
Product rule, point for that, does work. However, because this is a constant, I'm going to use the constant rule instead because it's just easier. How many knew it was constant rule? 2 points. Okay, so product is not wrong, but it's easier to use the constant rule. And remember, the constant rule is super simple. All it says is, there's a -3 here. It's going to show up later. So just remember that it just kind of tags along. Questions on that? Please.
What's the C and the F?
So in the rule,
Yeah.
this is what they're talking about. The rule states that d dx of a constant multiplied by some function is exactly the same thing as the constant multiplied by d dx of the function. So that's the idea of the C not really doing anything, it just tags along. So I can not worry about the C, I can just focus on d dx of what's left, what the C is multiplying by.
Okay, yeah, so yeah, I was just confused because it looked like it was C, F, and X, but it's just C and then F of X. It's only 2 different things. Right?
Let me look at it.
Like, yeah, see, it looks like it was 3, but it's just C and then f of x, it's only 2 things.
And then this f prime just means the same thing as d dx of f. Is that what you meant?
Yeah, no, it makes sense. I
Okay. I'm not doing a very good job. That's my fault. Happens.
So, when we're using the constant rule, we're just like kind of pulling the negative 3 out, right? And then we're going to use the power rule. For
There you go.
Is that what's happening?
It's perfect. Does that make sense?
Yeah.
Yeah. So what Hadley says is exactly what I'm going to do. The constant rule says just keep track of the negative 3. So I'm thinking, okay, I got the negative 3. I'm going to apply the power rule to the x to the 4. There is a little shortcut here that most people end up using. That is, the 4 comes down, do the power rule. You still got the 3 sitting there. So now you've got negative 3 multiplied by 4, negative 12. So combining the power rule and the constant rule, when you bring down the 4, you get negative 3 times 4, that's 12. Negative. We need to say that again. So the next line is going to look like this. Again, warning. I know that it's a bit tedious at first, but you must write what I'm writing. If you don't, you will get messed up. If you write what I write, I can pretty quickly start giving you shortcuts, and you'll be able to see them. But just, I know it's kind of a pain, but just write what I write for now. So I've got the negative 3. That got multiplied by the 4. That gave me negative 12. Okay, caution as well. I'm writing negative 12 times. We say negative 12 x cubed, but it really means negative 12 multiplied by x cubed. They're not together, they're separate. It's negative 12 multiplied by x cubed. That was using the power rule and the constant rule in combination. Please.
So, is that actually?
You good? 2 points. Anybody else?
I'm so confused why you use the constant rule.
Why?
Yeah.
Let me draw it differently, Hayden. So if I were to show the constant rule in combination with the, well, like separate, I would have written this. Negative 3, 2 points for Hayden, d dx of x to the 4th. Does that make sense? Do you see how I use the constant rule? Not really, that's okay. So right here I've got this one in pink. I've got d dx of a constant, negative 3, multiplied by what I'm referring to as f to be x to the 4th. Do you see that? Okay, then the rule says the constant can come out. So I put it right here. Okay. And then d dx of the x to the 4th. Thank you. Good now? Yeah. Good work. Please.
So you just did 2 steps and making 1 step.
I did. 2 points.
F of x is just whatever they're constant.
Right. When you're looking at the constant rule, what Avery said helps. The f isn't the original f. It's just as I'm using this rule, I just think of f as being, well, this constant is multiplied by what? Constant is multiplied by x to the 4th. That's the f temporarily, as I use the constant rule. Other comments? This is pretty good. Ellie?
When you got the negative 12x cubed, how did you get rid of the ddx?
Oh. So are you okay to hear?
Yeah.
Awesome. Can I erase the pink now? Everybody okay? So erasing the pink. That was exciting. Hit the right button. Let's get rid of this one too. The next line, oh, I still have d to the 4th, so we'll talk about that in a minute. So this is, oh boy. Good grief. Come on, back up, back up. Oh, shit. Forward. Sadness. Okay. Try again. All right, one more try. So this is d4 over dx. Okay. Next line would look like this. Okay, I need to get rid of this dx to the fourth dx, so I'm going to use the power rule again. So I've got dx of x to the fourth. You see it there, why I'm using the power rule. Okay, equal means same as. So that means I can replace this with this. So I do. The -3 is still there. I bring down the 4, have an x. This would become 4 subtract 1. This would become d over dx of this x. And I still have the d4 over dx. So that's showing a lot more detail. That would be like that. Questions to here? Somebody asked where the ddx went. I'm explaining that. So we're okay to this point. Well, dx over dx is just 1. So that's 1. There's no d dx here any longer because I just used the rule to get rid of it. That's the purpose of the rules, is to find some form that is more useful. Think of it this way. Right here, this side of the equation here is equal to dy dx, the slope of the function. We're trying to work our way through and find a formula. The shortcuts give us a way to do that and get rid of all the d dx operators. Other questions? Awesome. And then I said, hey, this is really -3 multiplied by 4 multiplied by x cubed. Therefore, we can write it as just -12 multiplied by x cubed. Oops, one more thing, sorry. Plus that d4 over dx. So questions to here. Awesome. Let's talk about this one. I do not have a rule for this. I have an explanation. Okay, derivative means slope. This means change in y divided by change in x. D means difference. So difference in y divided by difference in x. That means the 4 is a y value. It's a function whose value is always 4. So take your hand, finger, hand, whatever. Draw in the air, like here's a parabola, Draw a function whose y value is always 4. Good, good, good. Everybody keep doing this? Awesome. Everybody's waking up again. Awesome. It's very soothing, peaceful. Watch it. Never mind. Okay. This means tangent slope. So raise your hand if you can tell me, what is the tangent slope at every point of a function that looks like this? Hands up. What's the tangent slope at every point of a function that looks like this? Tristan?
0.
Raise your hand if you agree. Point. 2 for Tristan. So the derivative of 4 is just 0. If you don't want to write plus 0, I'm okay with that.
Would that be the same for any number in the top? So if the 4 was like...
Anytime you are taking, so I don't have a rule on the sheet, but what you're saying, Elijah, is if I were to create a rule, it would look like this. The derivative, d dx, of any constant is simply 0. So that's what you're saying, right? Yeah. 2 points. Anyone else? Awesome. Cool. Back to here. No ddx operators. So we have found a more useful form of f prime. F prime was this. This is f prime. Equal means the same. They're the same thing. This just isn't useful because I can't plug x's in. Here I can plug in x's. And if I plug in any x I want, I will find the tangent slope of f at that x. Question? Please.
Do we need to, like, can we simplify and multiply the negative 12x by the 3 in the front just because it's all multiplied?
So on the AP test, if it's the written section, 2 points for Hadley. If it's the written section, leave it like this. You can't stop here because you haven't gotten rid of all the ddx stuff. But here you can stop, but then you do exactly what you said, Hadley. If it's the multiple choice section, they're not going to have this as the answer. They'll say, wait a minute, 3 gets multiplied by this, gets multiplied by negative 12, gets multiplied by x cubed, and they'll start putting them together a little bit. So they'll say, oh, these two multiply to give me negative 36. They probably put the x cubed next, and then negative 3x to the 4th plus 4 squared. And if you turn the sheet over, the buff sheet, that should be the answer on the back. So you can check your work and just make sure you're not making mistakes. So, please.
Wait, why did you only do the 3 to that, to the 12, negative 12x?
Oh, versus doing it to the...
Why didn't you do it to that, to the first premises?
Like right here. Outstanding, 2 points. Pay the whole room, who knows why not? It's a really good question. Why did I not distribute the 3 into here? Who knows why? I'll pay everybody. It's a really good question. Why not? 2 for Brennan. Why not distribute? Like, it's actually not allowed, but why is it not allowed? Let's go, Isaac. Shoot. Ceremonial paying of the misnamed. Take the walk of shame. James.
Because it's squared.
Yeah. You can't distribute until we take care of the exponent. And they don't expect you to multiply this by this and then distribute, so you just can't. How many knew that? 0.2 for James. Okay.
Wait,
Rachel, please.
why is it x cubed in the front? Shouldn't it be x to the 8th or something? Because if you're looking at the... Do you square what's inside of the parentheses, the negative 3x to the 4th?
This one here?
Yeah.
So squaring means it would be this times this again. But I don't really want to write that, so I just leave it as squared.
Oh, that's right there. Oh,
Yeah, no, I just
yeah.
moved it.
Oh.
When you multiply things, the order doesn't matter.
Oh.
So I've got 1.
Okay, now I see what you did.
You see it?
Yeah.
2 points. Anybody else? Cool. Practice some more. So let's work on number 3. Looks good.
Wait, Mr. Smith, I have a
Yes.
question, sorry. So, you know how when you underline by the 3,
Yes.
see how the negative 12 and the x cubed is both underlined differently? Like the next one? Those two are 2 different ones, right? So when you distributed, did you only distribute to the negative 12?
Oh, awesome. Hey, 2 more outstanding questions. Look up. Everybody look up. Okay, really common mistake. So let's fix it so it doesn't happen. If I write this, please raise your hand if you know what belongs here. Come on, think with me. What belongs here? Hands up. And you could be sarcastic and do this, and I would have to give you points. What's an easier way of writing all that? What belongs here?
6
What?
times by 3. 6 times by 4.
Which is?
24.
There we go. I've set a bad example. Okay. How many knew that this was 24? Show me. 0.2 for Weston. Okay, watch me. When you multiply three things, you do not double multiply. You don't say 2 times 3 and 2 times 4. You simply pick any of the two. It doesn't matter. You can say 2 times 4 is 8. 8 times 3 is 24. You can say 3 times 4 is 12. 12 times 2 is 24. You can say 2 times 3 is 6. 6 times 4 is 24. So you don't double multiply. Distribution only occurs in this type of situation. But you still don't double multiply. Raise your hand. Well, never mind. It was going to come up, the question didn't work. To work this out, you have a couple of choices. In most of the problems we work, it won't be easy to combine these. So you can either go this times this times this. That would give you this situation. And then you can distribute the 2. Okay? But don't ever double multiply. You don't go distribute the 2 and, well, it's like combine these first, then multiply by 5. Multiply these two first, take the result, multiply by 4. So back here, same thing. I've got this times this times this times this. I can't distribute anything, so I just chose to multiply these two, and then the rest I just wrote down. So that's all I've done.
So you kind of looked at like negative 12x to the cube, like is just one thing?
No, I looked at it as two things. I've got negative 3, this, negative 12, and this. I chose to multiply these two together so I could write negative 36. I chose to put this multiplication in the other order. The x cubed is not attached to the negative 36, everybody. Don't attach this to this. They're not. They're just two things multiplied. There's nothing wrong with writing this. Same thing. Does that answer your question? No.
Kind of way. So, you only distribute what's outside the parentheses to the inside of the parentheses. If there's like a plus or a minus in between it, that's what I
Yeah.
think, right?
So there's no distribution here.
So you wouldn't say negative 36 times 3x to like 3. You wouldn't like, because it's like kind of just, that's what I mean. So it isn't one thing, but it like is when you distribute it, right? You know what I mean?
In this case, there is no distribution.
Except to the negative 12.
That's still not distribution. Distribution is when
you're just timesing.
just choosing. I'm just choosing the order of multiplication.
Because they're on each side of that first parentheses.
There are 4 things being multiplied. I get to choose the order of multiplication. That's all I did.
Okay.
It's not distribution. Distribution is when you have something multiplied by a sum. Then it must distribute. But we don't have that. We have 4 factors. Factor times factor times factor times factor. Kes?
Would you be able, if you wrote out negative 3x to the 4 plus 4, you wrote that out into 2 parentheses, so it wasn't squared anymore, then you could distribute?
If I do this, correct, Cass? That's what you're thinking?
Yeah.
If I have this, I now have 1, 2, 3, 4, 5 factors. I still get to choose the order in which I want to multiply those factors. So I could choose to multiply these two first. That would require distribution because the x cubed would have to go to both. That would create a new factor. And then I'd have 4 factors to multiply. With those resulting 4 factors, I get to choose how to do it. Is that your question?
Yeah.
Brendan, have I helped at all?
Yeah, so the reason that your answer is what it is just because that was the easiest way to like multiply those factors together.
Actually, it's just because I knew that was on the back.
Yes, so it's just like you have to like get
It's
to
totally
this.
random. I just gotta make sure I'm doing it right, so I just gotta check the back and say, oh, that's what the back did, but that makes sense, so I'm okay.
Okay.
This is a perfectly good answer. There's nothing wrong with it. Okay, cool. Next one. Go to number 3. So 3 says inverse cosine. Five x to the 5th, is that correct?
Yeah.
So the goal is to find the derivative. So I ddx both sides. I differentiate both sides. And then I go looking for a rule. So don't look too hard, but please raise your hand when you can see which rule applies to ddx of this. Looking for the other half of the room to raise their hand. So which rule applies to ddx of this right here? So Chase?
Inverse cosine.
So the inverse cosine rule says, let's see, d of inverse cosine of whatever is equivalent to -1 divided by square root 1 minus whatever squared multiplied by ddx of the whatever. So how many knew it was this rule? Point. So applying that, this becomes, this is just dy dx. You can abbreviate that as y prime if you'd like. This becomes -1 square root 1 minus the something d of that same something.
Well, why do you have the 5x to the 5th on the bottom? Where's the...
Oh, I wrote that wrong. Hold on. That's my bad. 2 points for Brennan. Does this look better? Perfect. Questions? Please, Hayden.
Do you ever like take the, like do the power rules with funnels?
Right here.
Yeah.
I will. So it's very similar to what we did a minute ago. I've got the multiplying constant 5, because remember, it's not 5x to the 5th, it's 5 multiplied by x to the 5th. They're two separate factors. So the multiplying constant's just going to tag along. I can apply the power rule to the x to the 5th, which means the 5 comes down, multiplied by the constant will give me 25. So now I have this. Question. Please.
So, you know how on the power rule it has that second part, d over d, like, you know how on the last time that we did it, it had d of x over d of x and that just equaled 1?
Uh-huh.
Does that happen again right here?
Absolutely.
Can you show that? Like,
Uh-huh. So using the rule, the 5 comes down. It's now I'm combining the constant and the power, so that gives me the 25. And you have x to the 5 minus 1. Then you'd have d over dx of just the x. But dx divided by dx is something divided by itself, so that just equates to 1.
Oh, so it doesn't matter what power it is, because the little parentheses that you have is the x in between, it's not the
In
x.
this case, yes.
Okay.
Wait, can you
Please.
go over that just one more time? How you got the dx over dx?
So the rule says you have d of something to a number, get number times the something to number minus 1.
Yeah, so that's where the 25x to the fourth comes from. But where does the dx on the top come from?
This one here.
Okay, wait, is that x kind of like the x that how it went from 5 to 4? Or
Not
how'd that
quite,
happen?
you're
Okay.
close. Let's stay with me for a minute. So remember, the 5 is the constant rule, so ignore that temporarily.
Okay.
So what I've really got here is d of x to the 4.
Okay.
So the 4 comes down.
Mm-hmm.
This is x. This is 4 minus 1.
Mm-hmm.
These are all the same thing, so this is x.
Okay.
So that's the dx dx.
Mm-hmm.
The 5 that's right here gets multiplied by the other 5 to give me 25.
Okay.
Sure?
I think so.
Anybody else? 2 for Rachel.
I don't know.
Okay, one more time. Hold on. So here's what happened. We're working on this right here. Here's all the details. First thing I do, so you've got d 5x to the 5th over dx. I use the constant rule first. Are you all okay to there? The next thing I do is I'm going to use the power rule. So here's the 5, leave that there. Power rule says bring down that 5. Is everybody okay with that? Then you have x, new exponent. Everyone okay with that? Multiplied by d dx of this. See it? Anybody else?
So ddx of what? Because I understand like
Okay.
how you get the dx over dx.
Here's the rule. Okay, so okay with the rule? In our case, we're applying the rule to this right here.
Yeah.
So we have an x here, which means that same x will show up here and here,
Okay, that was
because the parentheses mean the same thing. Good there? You good now? Anybody else? Awesome. We good to hear? dx over dx is 1. Okay, now eyes on the board. Come on. Okay, when you see a big fraction like this, make sure you see it correctly. What you should see is I have a large numerator and a denominator. The numerator is comprised of -1. Again, these aren't together. Don't put them together. We just wrote them next to each other. They're not like a thing. Okay, they're just. Is that the right word? Okay. What do you call when two people are? Never mind. Okay. So -1. They're not a couple. Look, -1 multiplied by 25 multiplied by x to the 4th. You can multiply the 3 in any order you like, but it's kind of traditional to say, hey, let's multiply the two constants. So -1 multiplies by the 25 to give you -25. Oh, x to the 4th still. Question?
That was just the easiest way to do it, kind of.
I have to be honest, it's not necessarily easiest, it's just traditional. That's just what everyone's done forever. Doesn't mean it's right, it's just that's what they use. This answer is plenty good. Nothing wrong with it. This is the written section of the AP test. As long as you don't write dx, because that's just one, they would give you full credit for that, just like this. Okay, next thing. Oh, please, have it.
Well, I was going to say we could simplify
This one here. What would you do?
Well, I was wondering if you could put
The 2, like remove it. So you're thinking this as this. Okay, let's explain. Look out, hey. Okay, what Hadley just asked about is a very, very common error. So again, I want to fix the common mistakes and just get rid of them so they don't get in your way. Calculus is tough enough with like messing up with algebra at the same time. Okay, one reason I hate this word is this situation. Many people will look at this and say, wait a minute, square root cancels with square. Like, I don't know whoever said that, but okay. Sorry, it makes me upset. Don't do that, okay? Square root does not cancel with square. That's why we don't use this word. This is the square root of, one second, strike. This is the square root of 1 minus that thing. Square root means you got to go figure out what times what would be this. That's not easy, so I'm not going to. Sorry, question?
So is the reason we can't cancel it is because it's 1 minus the thing that has the square root?
Think of it this way. So I still don't like the word cancel, but 2 points for a good question. Think of it like this. If I had the square root of 5x to the 5th squared, I still would not think cancel because I don't think that makes any sense. But I could ask myself this question: what times what is equivalent to this? Oh yeah, I got it. If I just multiply this by itself, I would get that. So I'm finding the square root. I'm not canceling anything, I'm finding the square root. I hate the word cancel. Bad. Good? Awesome. Okay, back here. But I do want to give you a hint. When you take the next test, if you'd like to miss a question and just start with 97, just don't listen for the next 30 seconds. If you'd like to make sure you're not going to miss this question, listen close. Said with some sarcasm. Okay. To square something does not mean just apply the 2. That makes no sense either. Squaring means multiply by itself. So this is really 5x to the 5th multiplied by 5x to the 5th. So you'd have, let's see, 5 multiplied by x to the 5th multiplied by 5 multiplied by x to the 5th. That's 4 factors that need to be multiplied, and you get to choose the order. So it's traditional to multiply these two, giving you 25. And traditional to multiply these two, giving you x to the 10th. So yes, you can rewrite this result, if you so choose, like this. And I believe there's a test question that requires you to know that. Oh, yeah. So 1 minus 25 x to the 10th power. Question? Please.
So that's the answer just because that's the answer that you decided to have simplified on the back.
Yeah. So like, is that on the back?
Yeah, but so it's like for AP tests and everything, the answer is just when you end up getting rid of the d over dx.
Right. On the written section. On the multiple choice, you've got to see what answers they present, and they may not present this as an answer. Then you'd have to know that this is equivalent.
So like on this in our homework, we just have to get to the point where d over dx is gone and then see what your answer is and see what you use.
Perfect. Perfect. Okay, now no homework tonight, though. Yeah, no homework tonight.
Oh, let's go.
So we don't have to do that yet?
We'll make up for you. just like it's during the retake session.
As far as like politics go, I feel like I'm probably just because
Yeah, I really have.
you're like,
So anytime you have, so you get the text message, yeah. So anytime I have a retake prep session, you can sign up for one of those spots and come and
Two more until.
wait, so like
1.5. Oh, it's Thursday.
part of what I'm doing is